Okay, it's Mr. Benson here with the third video, which is looking at electric power. Now again, electric power is one of the two bigger units, so like motion, this one's reasonably large. Okay, so a lot of the questions are the same sorts of styles that we've seen quite a lot of. Two identical solenoids are placed side by side. The solenoid on the left has a steady current, blah blah blah, as indicated by the arrows on the solenoid on the left indicate the north end of the electromagnet. So what you've got to remember here is north is where the field lines are coming out of the solenoid. Now this is one where we're going to use our right hand grip rule here. And when you put your right hand around this wire here, so your thumb is going to be downwards and your fingers are going to be pointing out of the end of that solenoid like that. If you don't believe me, you can double check it at the other end and you'll find that your fingers would be pointing into the solenoid, and so the north end of the magnet is here. So that's our first mark. Now the magnetic field produced by the solenoid is very weak. Give a way to increase the strength of the magnetic field. Now my favourite two answers are to add an iron core or to increase the current. I think if you were to increase the number of turns, that's also an acceptable answer. The thing I don't quite like about that one is that you're actually then changing the solenoid. Although it's not unreasonable, but the first two things you can do without actually changing the solenoid, but you can increase the strength of the magnetic field. Okay, the magnetic field lines created in the left solenoid pass through the right hand solenoid. Does this induce a current in the right hand solenoid? Explain your answer. The answer is no. So that is probably 1 mark. You don't need an exclamation mark there if you don't want to. Now the reason for that is that the EMF is proportional to the change in flux, and there is no change in flux here, so we can say that the change in flux is 0, so the EMF is 0 volts. Okay, moving on, we scroll down. So now we've got similar question here, but some slightly different ideas. So the iron bar is placed through it, so we now have an electromagnet effectively. Now when the switch is closed, a large current flows through the solenoid. As a result, the copper ring is... Now what we've got to think about here is what's going to happen in this situation. So a copper ring can have a current induced in it by the magnet. So what we've got to think about the direction that that's going to go in. Now in most respects the setup is the same as in our original question, so we have the north end of the magnet is in this direction. Now when the magnet is when the switch is closed and the current flows, the flux is going to increase to the right. Now there's a couple of things you can think about that one here. About what's going to happen here, this is going to create a current which is going to oppose the change in flux of the other magnet here. Now it's kind of an interesting question because it doesn't matter which direction that flux is going in, it's always going to oppose it. So basically the effect of that is that this copper ring here becomes a magnet temporarily because it's opposing the change in flux from the first magnet. So we get field lines which are going in that direction. Now effectively that means that the north pole of the copper ring is going in the opposite direction to the north pole of the electromagnet, and we all know that when you get the north poles of magnets and put them against each other, they will repel. So the answer there is D. Now you can kind of answer that one without really thinking about the direction of the induced EMF or any of that stuff either. The only thing that's important here is that the induced flux is always going to oppose the change in flux. So this is the sort of question though where you might also get asked about the direction of the EMF, and there's a couple of ways you can think about that one. You know that, well, if the flux is increasing to the right, then the induced flux will be following this arrow here, and you could use your right hand grip rule with your fingers following this line here, and you would see that the current was going around in that direction there. The other thing to do with a question like this where you don't need to use any explanation, if you use the left hand rule that I invented, where your thumb points in the direction of the increasing flux, then your fingers are curling around in the direction of the current in the ring. But this question isn't actually answering you for any of that, asking you for any of that. Okay. Now the next question is an interesting one. When the switch is, it's replacing it with an iron ring. When the switch is closed, a large current flows through the solenoid. What is the best description of the behavior of the iron ring? Now, we can think about, well, all the stuff that's happened here. Now, we know that it's a metal ring. It's going to have an induced current, and that's going to oppose the change in flux just for that very early period when the switch is closed and the current increases in the circuit. So D is true for a very short period of time. The other thing we know about an iron ring though is that it's going to have induced magnetism. So the all the magnetic dipoles in the iron are going to align, and they are going to align in the same direction as the electromagnet, which means that after the switch is closed, the iron ring is going to act like a magnet that is going in that direction. So it is in fact aligned with the electromagnet. So the south end of the iron ring is aligned with the north end of the electromagnet, and it will be attracted. So the best answer here is actually A, because that is what happens most of the time. At the start there would be a very small repulsive force from D, but then it's going to be then that force will disappear anyway, but it'll also be overcome by the attraction there. So our best answer for that one is A. Alright, moving along here to some induction questions. A square coil of area A is pulled with constant velocity across the field lines, and we've got to choose the best EMF and the best change in flux graph. So which best represents the change in flux? So the answer for that one is A, because we start off with no flux in the square coil, then it increases as a linear fashion as it moves into the field. Then while it's moving across the field, the flux is constant because the whole area of that coil is in the field there. Then it moves out of the field and the flux decreases in a linear fashion. So down to our first question here, which of the first choices represents our flux? Well, that one is A. Then for which represents the EMF, the EMF is proportional to the change in flux, or the gradient. Now when we look at this, the gradient here, although this is slightly unrealistic, the gradient here is a constant positive value from here to here. It's 0, and then it's a constant negative value from there to there. So this matches up here, and this matches up there. The best one for this question is C. I doubt they'd ask you anything much more complicated than that. Okay, moving on to a transformer question. So we've got 120 turns on the primary side and 480 turns on the secondary side. Now that immediately tells me that I'm going to get a higher voltage on my secondary side because I've got more turns. We've got a 2 kilo ohm resistor on the secondary side. We've got a current of 2.4 milliamps RMS passing through it. So what is the power dissipated in the 2 kilo ohm resistor? I know my current and I know my resistance, so all I need to do here is just use P equals I squared R. So 24 times 10 to the minus 3 is my current, squared times 2 times 10 to the 3, and I get 1.15 watts, or we'd probably say 1.2 watts in our answer there. I wish I could do dots on this thing. Okay, what is the input voltage on the primary side? Now, I know I know the current and I know the resistance on the secondary side, so I can work out V secondary is IR, which is 24 milliamps times 2000 ohms, and I get 48 volts is my output voltage. Now, my input voltage is going to be 48 multiplied by the number of turns in the input side over the number of turns in the output side, and I get 1.2 volts. Now, I'm not even really thinking about the formulae here for transformers. All you've got to remember is that you're going to have the highest voltage on the side with the highest number of coils and lowest on the lowest, and you've just got to ratio those correctly. So 1.2 volts is my answer there. What is the RMS current in the primary coil? Now, again, similar sorts of things, except it's opposite. I'm going to have a higher current on the side that has the lower number of turns. So I primary is going to equal I secondary times the number of turns in the secondary divided the number of turns in the primary, because it's going to give me a bigger value, and that works out at 0.96 amps. So all these questions really are is just putting the right values in and getting your ratios right. What is the power supplied to the primary side of the transformer? Now, this is possibly a stupid question or possibly a trick question. I couldn't quite figure out which one it was. This question, although they don't say it's an ideal transformer, they give you no information to suggest that it's not, or that would allow you to calculate anything else. So the whole point of an ideal transformer is that the power, actually I will use this line now, power on the primary side equals power on the secondary side. So when we have a question like this one down here, what is the power supplied to the primary side? It must be the same as what was being used on the secondary side. If they'd given some information about efficiency or something like that, then maybe we could have done a calculation there. Okay, the purpose of the soft iron core is to, I would say a good answer there is to give maximum flux through the secondary coil. Through the secondary coil. Something along those lines. Then we get question 15, a DC motor question. We're given a whole lot of information about this. Now, you've got to be careful with these because people tend to drop stuff. The biggest mistake in this one was omitting information like the number of turns. Be careful with the prefixes on these as well. A mistake I saw a few times when I was marking this was people who just dropped the millis, or that was probably the most common one. The magnitude and direction of the force. Well, let's start with the direction. Now, we know that our field lines are going from north to south like so. Our current, well, is flowing in here and is running from X to Y like that. So all we've got to do is use our right hand slap rule or right hand force rule. Now I use the one where my fingers are going in the direction of the magnetic field from left to right. My thumb would be pointing along the arrow from X to Y, kind of into the page, and that means that the force on this wire must be going downwards. Now that means that our rotation will go anti-clockwise, but I'm not sure they ask us that. So the force is down. That is our direction for this question here. Okay, the magnitude. Well, all I've got to do here is go F equals NILB. And I've just got to be careful that I put everything in. So N, a bunch of people forgot that. I is 50 times 10 to the minus 3. L is 400, again, times 10 to the minus 3. And B was 6 centimeters, so it's 6 times 10 to the minus 2 because everything's got to be in meters. And we get 0.48 newtons is our force. Okay, explain the purpose of the commutator and the operation of this motor. Something along the lines of, so to change direction of current, every 180 degrees, to give continuous rotation by, actually, sorry, this is terrible. I would suggest you have a look in the solutions when I post them online shortly, but you know the sort of stuff that they're after here. I would prefer to spend my time on the calculation questions. But what you're really looking for there is to say that you're changing the direction of the current in order to change the direction of the force on the rotor to give continuous rotation. Give two simple ways to increase the speed of rotation of the motor. Now, there are two good answers and one that I probably, again, don't like as much because it involves actually changing the motor. Okay, increase the current is one. Increase the magnetic field is another. You could argue that that possibly involves changing the motor. And the other one is increasing the... oops, sorry, I probably should have made that little n there. Increasing the... that's not very helpful. Increasing the number of turns. Okay, moving down. Now, the next question is a little bit of a left field kind of question because it's thinking about a little bit about the stuff that we would have learned about in, Unit 1 or in Year 11. So you might even remember some of that stuff from then, but you can also figure out some of the stuff from what we know about the movement of charged particles through magnetic fields. Now, label the paths X, Y, and Z. So what do we know about these? Without doing too much thinking here, gamma rays have got no charge, so they're not going to be affected by a magnetic field. So that means Y is going to be there. So Z and X are our next two choices. Now, what I know about an alpha particle, well, it's got more charge than a beta particle, but it also has much more mass. So although it's got more charge, it won't actually deflect as quickly because it doesn't accelerate as quickly. So this one must be Z, and the beta particle over here must be X, because it deflects very quickly in the magnetic field. Now, the value of the following ratio: magnetic force of the beta particle on the magnetic force of the alpha particle. Now, if you think about this one here, the equation that we're thinking about here is that the force equals VB. No, it doesn't. Completely wrong. The force is QVB. There we go. Where there's our charge, there's our velocity, and there's our magnetic field. Now, this is a constant, so the only things we need to worry about here are Q and V. Now, when we think about our whoops, sorry about that, jumping around a little bit here. When we look at these two, well, we can see that the beta particle is traveling 3 times as fast as the alpha particle, but it has half the charge. So what we could say about those is that the beta particle is going to be, well, it's got a charge of 1 and it's got a velocity that's 3 times. The alpha particle has a charge of 2 and it's just got, well, 1 unit of velocity relative to the beta particle in this case, and so what we end up with is 3 over 2 or 1.5. I kind of like this question. It's a little bit out of left field, but you can you just need to think about the equations and how we can apply them. Alright, moving on to a pretty classic electric power question, although there's quite a lot of information in it here. What is the current flowing in the 0.5 ohm cables? Now, what we've got here is that we know that we've got 2000 watts and we've got 2000 volts. Now, in order for that to happen, then all we've got to think about is I equals P over V, which is 2000 over 2000, and so we have a current of 1 amp flowing there. How much power is lost in the 2.5 ohm cables, which means we've actually got a resistance of 1 ohm. Well, there's a couple of ways we can think about this one. The easiest one, again, is just to go, or the shortest one perhaps, is to go P equals I squared R. So we've got 1 squared times 1, which gives us 1 whole watt. So the answer there is 1 watt is lost. What actual voltage is delivered to the step-down transformer? So now what they mean here, and this gets kind of confusing. By the step-down transformer, yeah, well, actually, sorry, it's not confusing because it's on the diagram, but you've got to think about this here. So we've got the step-down transformer here. Now, there is going to be some voltage drop across these cables because that's what happens. So we need to think about what that will be. So V equals IR again. Now R, remember we've got a total of 1 ohm resistance for the cables. Our current was 1, so it's 1 times 1. So we've got 1 volt lost, or 1 volt worth of voltage drop. So we're going to have 1999 volts supplied to the step-down transformer. What is the ratio of, sorry, I've gone a little far there. What is the ratio of the primary to secondary turns in the step-down transformer if it delivers 240 volts RMS to the house? All we've got to think about here is that we're going to have less turns in the secondary than we are in the primary. Now, it's kind of a weird question, this one, because we've got these numbers that don't have any common factors in them at all. So our input voltage is 1999 and our output voltage is 240. That is the answer. That is the ratio, because we can't simplify that one. Okay, and again, that is the end of electric power. I will be back shortly with the next video on light and matter, and then there will be one on